Section 2. Cameras. In this chapter we discover how different types of camera work and how a camera records an image. We then look at sensor size and the number of pixels. And finally we look at metering, exposure bracketing and exposure tricks. There are essentially two different types of modern cameras. The first is the DSLR, which stands for Digital Single Lens Reflex Camera. This is the digital version of the SLR, which hit the shops in the late 1950s. The main advantage of an SLR over a rangefinder camera is that you're actually looking through the lens. You get what you're looking at. This is possible because there's a mirror in the camera. This is placed in front of the sensor and reflects the image onto a pentaprism. This in turn reflects the image to the viewfinder. When the shutter is released, the mirror flips up, exposing the sensor to light. The shutter speed of a DSLR is limited by the mechanics of the mirror. The latest generation of cameras are mirrorless. They allow light to fall on the sensor whenever they're switched on. The image seen through the viewfinder is effectively a video render from the sensor in real time. When you press the shutter, the camera's sensor is turned on and off for the desired time. The benefits to mirrorless cameras are that they are smaller and lighter, as they have no moving parts and they can achieve higher shutter speeds and more frames per second. The optics and resolution of both cameras is currently similar, but manufacturers are now concentrating on mirrorless cameras and lenses. For example, Canon no longer manufacture EF lenses, and the majority of their latest models are mirrorless. Before we start, I'd just like to say the following description is a simplification of what actually is going on inside a digital camera. However, it should get over the principles, and if you want more information, then Google's your friend. We start with light or photons from the subject entering the camera through the lens, where it goes through a series of optics and the aperture to land on the sensor. In front of the sensor is a red, green and blue mosaic filter known as a Bayer array. It's not important to remember the name, but it's worth knowing how it works. If you hold a piece of red tinted glass up to your eye, all you would see is shades of red. The job of the filter is to screen light into one of the three colours. This filtered light then hits the sensor, which is a matrix of millions of cavities known as photosites. If you think of them as buckets and the light hitting them as water, it makes a bit more sense. Whilst the shutter is open, the photosites fill with varying amounts of photons. When the shutter is closed, the number of photons in the photosite causes an analog voltage. This is a bit like weighing a bucket of water on an old-fashioned set of scales. This analog signal is then amplified. The amount of amplification is determined by our ISO. So if the ISO selected is 100, the signal is not amplified. If the ISO is 400, the signal is amplified by a factor of 4. It's a bit like turning the volume up on a record player. Finally, our analog signal is converted by an analog to digital converter, or ADC, to become a digital value. It's a bit like weighing our bucket of water with a digital scale. Now that our signal is digitized, the three RGB colours are merged to form a colour pixel. All the pixels from the entire sensor constitute a raw file. Attaching to this is the EXIF information like date, time, camera, lens, and exposure information, etc. Cameras also produce JPEG files of varying resolutions to send to the electronic viewfinder as well as the screen on the back of the camera. If required, the camera will also produce a full resolution JPEG file. Finally, the files that are to be saved are placed in the buffer. This is like working memory, much the same as RAM on a computer. The files that are in the buffer are then saved to the SD card. The reason for the buffer is that some cameras can take images so quickly there isn't time to store the files on the SD card in real time. It simply isn't that quick. Some mirrorless cameras can shoot 20 frames per second. That's about 1 GB of data per second. The diagram below shows the most common digital sensor sizes to scale. On the far left we have the tiny sensor found in high-end digital mobile phones. In grey we have full frame. It's so called because it's exactly the same size as used in traditional film cameras, which is 24 by 36 millimeters. At the far right we have medium format, which is larger still. From the table there is some key information. The new Samsung S23 has a whopping 200 megapixel camera. However, this is only in JPEG format and its raw images are only 50 megapixels. Whilst this number of pixels is impressive, it isn't everything. Remember the buckets analogy? Well, if you have small buckets, the amount of light collected is equally small, which makes errors more likely. Furthermore, the optics of any mobile phone cannot match those of a proper camera. I think the majority of the class shoot with an APS-C camera, commonly known as a crop sensor. This is around 38% of the area of full frame sensor, which is dimensionally 1.6 times larger. In my opinion, the number of pixels you have is more about the ability to crop an image. Here I've taken a photo of a sea eagle, which is beyond the reach of my 200mm lens. However, with a 102 megapixel camera, there's plenty of room to crop in heavily. Here we have the final image, which is still 9 megapixels. This will print on a 13 by 13 inch square perfectly. Just for fun, I've finally cropped the image to the resolution that will fill an entire computer screen. You don't need many pixels unless you're printing large and the viewer is looking at the print with a magnifying glass. As most viewers stand back to look at a large print, the number of pixels in your picture is seldom an issue. Most home and commercial printers print a resolution of 300 dots per inch. This is invisible to the human eye. To print every pixel on a standard 6x4 inch photo, the image only needs to be 1800 by 1200 pixels, which is just over 2 megapixels. For a 12 by 8 inch print, you only need 8.6 megapixels. We've already looked at the exposure value scale and measuring exposure value in this course. Cameras all come with a built-in light meter. When we press the shutter release button halfway down on our camera, it measures the light in the scene and displays an arrow to indicate if the exposure you've selected is underexposed, overexposed or spot on. The numbers -3 to +3 indicate the number of stops that the exposure is out by. This is a really handy tool for getting exposure right. However, it doesn't mean that you will always get what you're expecting. To understand why, we need to understand what our meter is doing. Cameras have become increasingly sophisticated. Most cameras have 3 or more metering modes, but the principle remains the same. Meters measure luminance, that is, they measure light intensity, not colour. So if we turned our pictures into black and white and averaged out all the colours, we would end up with either a black, white or some shade of grey image. When we get our exposure right, the average is middle grey. This whole picture approach is called evaluate metering. However, there are sometimes flaws in using this approach. If you look at the 3 squares at the bottom of the page, you can see that they would all average out to a mid-grey. To address this scenario, the camera has centre-weighted metering mode, where only the centre portion of the frame is metered. And finally, the camera has spot metering. This is where you point the centre of the frame at the light source you want to measure, then you set your exposure, and then you recompose the frame. It's worth noting that the perfect exposure will not stop your highlights burning out if there's huge contrast in the scene. On most digital SLRs, you can take an image and then view the histogram. On mirrorless cameras, you get a live histogram. Histograms are bar charts showing the number of pixels on the vertical axis against brightness on the horizontal axis. In the diagram here, the white histogram is displaying the luminance or brightness. The number of black pixels in the photo are shown on the far left of the graph, and white pixels are shown on the far right. If our histogram is bunched up on the left-hand side, our image will be very dark and the black pixels will be present. Conversely, if the histogram is bunched up on the right-hand side, our picture is overexposed and we are blowing our whites. As you can see from this histogram, the pixels fall between the extremes of black and white, and we therefore have an acceptable exposure. Below there is a separate histogram for each of the red, green and blue channels. Every histogram is unique, so there's no recommendation as to the shape of the histogram. What is key is that the pixels are not touching either end, especially the whites. This would indicate that the photo is blown. A recommended technique for using the histogram is to shoot to the right. That is, get the bars almost touching the right hand side but not quite. In this histogram, you'll see that the graph is touching the right hand side. This indicates that it's overexposed and white is present. Some cameras show blinkies or zebras. These are highlight alerts. They show areas of the photo that will blow out and you need to reduce your exposure accordingly. Once you get to grips with histograms, it's a fantastic way of exposing your image. Although these can only be viewed on a digital SLR after the image capture, a quick check of your histogram will tell you if you've blown the photo. More importantly, you still have a chance to take another shot. So far we've talked about photos where we can fit our exposure within the dynamic range of our cameras. Remember, the dynamic range of our camera is 7 to 12 stops, and our eyes can see 20 stops. There are plenty of times where the contrast in the shot exceeds our dynamic range, especially when the sun features in the frame. The only successful way to deal with this is to take multiple shots using different exposures to span the dynamic range. Most digital SLRs have the ability to bracket exposures, and I'll demonstrate how this is done, but basically the camera takes 3 or more images by varying the shutter speed to get plus, 0 and minus exposures. Here we have 3 bracketed shots that made up the image on the right. The first image is at 0 EV, the next is 2 stops underexposed, and the last image is 2 stops overexposed. There is real value in taking this approach. The base image has much of the detail, but the cliffs are too dark and the sky is too bright. The underexposed image has retained all the colours in the sky, and the overexposed image has all the shadow detail. Once you get home, the photos can be merged in software to form a single image. This is called HDR, or High Dynamic Range Photography. Exposure compensation is a way of fooling your camera into thinking there's more or less light. For example, if I wanted to take a picture of a person, my camera could automatically set the exposure for the frame. However, what if I wanted a much darker image so that the subject was silhouetted against the background? Well, if I was using manual exposure, I could drop the exposure a couple of stops and I would get the desired result. If I was shooting in automatic mode, this is not possible. The solution lies with exposure compensation. If I dial in -2 stops of exposure compensation, the camera continually takes photos at 2 stops below the recommended exposure. For your information, exposure compensation changes the shutter speed, not the aperture or the ISO. So it's particularly handy if you're shooting in auto or aperture priority mode. If you're taking a panorama, you want exactly the same settings to be applied across each frame. To achieve this, you can press the exposure lock button, and each shot thereafter will be using the same settings. Don't forget to turn it off when you've finished.